Now that we have seen some of the overall requirements of a battery management system, we are going to go back and review some of the battery models that we looked at in the previous course and give a little bit of introduction as to why that's the case here. And in this chapter, we also look at some more advanced topics, such as being able to simulate the application and simulating battery packs as a whole. When we looked at the functions of a battery management system, we saw that some of the more advanced control-oriented functions, including being able to compute estimates of some fundamental quantities inside the battery pack, and these include things like the state of charge of the cells of the battery pack, the state of health of the cells of the battery pack, and even maybe state of life. Furthermore, there were some quantities that we could derive from those that were really important, like the power that an application could derive from the battery pack over the next few seconds, and the available energy in the battery pack, which would give you some indication of a range of a vehicle or an application, time to empty kind of information. In order to compute these estimates, the best available methods use models of cell input-output dynamics, and a model is simply a set of equations that describes how something operates. We can get by with models that describe input-output relationships. We believe that future applications are also going to require insight into what happens inside of this cell, additionally to the input-output dynamics, to be able to predict and minimize degradation, for example. And so there's different kinds of models of battery cells. We saw two fundamentally different models last semester, and we're going to very briefly review those two models here, and then we're going to proceed with the rest of the course. The first type of model is an equivalent circuit model of a battery cell, and this is an empirical model. It's a type of a curve fit that collects data in the laboratory and projects that data onto a set of equations that then you find the parameter values, the numeric values of the unknown constants in the equations, and you get this curve fit. And because we're using the type of equation we're using that we're projecting onto as a circuit model, we call this an equivalent circuit model of a battery cell. So we're doing a curve fit, and all of the kinds of pros and cons of curve fits apply to equivalent circuit models. One is that interpolation among the data is usually done pretty well by a curve fit, but extrapolation beyond the data that's actually been collected when fitting the model is not reliable at all, or it may not be reliable. It's just we don't know how reliable it's going to be. We can predict input-output behaviors of the battery cells well, because that's the kind of data that we collected. But the data we collected when performing the curve fit did not include internal electrochemical states, so we have no ability to predict that at all. The circuit models give us robust simulations in the sense that the simulator doesn't crash. The simulator will always run and give us some result. We just don't know if we're extrapolating how reliable that result is, and we can't predict internal states, but the simulator is not going to crash. And the simulator using the model is also going to be quite fast. There's a very small number of equations with a very few number of unknowns, and it executes quickly. The other type of model we looked at was a physics-based model, and instead of collecting data and essentially doing a curve fit that seemed to work empirically, we went all the way down to first principles to describe how we believe the battery cell operates, and we came up with physics equations. And we measured certain things inside of the battery cell. We measured diffusivities and conductivities and so forth using specialized lab experiments to do so. And then we came up with models. And these models, because they're based on physics, can predict over a wide range of operating conditions, not just whatever we might have happened to collect data for in the lab for the circuit models. We can predict internal states or internal variables of the cell, which is going to be useful for predicting aging. But the models are generally partial differential equation models, and partial differential equation simulators sometimes fail to converge and sometimes don't give robust predictions simply because it's a much more complicated simulation environment. And the simulations tend to be quite slow, especially when compared to an equivalent circuit model. So there's pros and cons. These are fast, they're robust, but they may not be as accurate or as predictive as we like. These are slow, these are not robust necessarily, but they can predict the kinds of things we want to predict, we believe, more accurately. So last course we studied both types of models, and furthermore we saw how to produce a reduced order physics-based model that has similar complexity to an equivalent circuit model. And that was the best of both worlds, because the reduced order physics-based model gave us fast simulations, it gave us robust simulations, but it also gave us all the predictive capability that we were looking for. So, great, we've got these physics-based reduced order models. We're going to use them now, right? Well, not yet. This course, as we've mentioned, really focuses on applications of the empirical models to battery management, of the circuit-style models to battery management. Next course, when the next course is developed, we'll focus more on the physics-based models. This is still more of a research area for us. It's tricky to find all the parameter values of a physics-based model without having a fully equipped lab full of electrochemists and material scientists. So can we get good parameter values for physics-based models if we have the kind of lab facilities that we assumed for an equivalent circuit model, which is far more common? Can we do power calculations? Can we do SOC calculations? We have answers for some of these things now. We're still doing research on some of these things, but I hope that we can introduce a course on all of these things sometime in the future. Nonetheless, we are going to review both models because we will refer to both models over the course of the semester. It's just that our focus is going to be on the circuit type of model. We're also going to apply the circuit type of model to simulating battery packs in this chapter. So the first approach is an empirical modeling approach. If you collect a lot of data, especially using simple tests, so the data can be visualized in a way that might be helpful to understand how a cell works, it appears that the current to voltage behavior of a lithium-ion cell is fairly simple. And in fact, it often is well approximated using a circuit as an analog. And the empirical models are used extensively in real-time control algorithms. I would even say exclusively, except I don't know every manufacturer's product line. I don't know what every manufacturer is using right now. But to the best of my knowledge, equivalent circuit models at this point in history are the only type of models that are being used in battery management systems. Again, I believe that's going to change, but that is this course is still state of the art in that sense. Last course we looked at something called the enhanced self-correcting cell model. And that's just a name that I gave to it when I was developing it many years ago. But it's very similar to equivalent circuit models used by a lot of researchers and a lot of literature. This is just the name that I use. The model is drawn in the diagram to the right. The features of the model, it includes open circuit voltage of a cell that depends on state of charge being Z. It includes a hysteresis component. It includes a series resistance, and it also includes one or more resistor-capacitor pairs, themselves wired in parallel, but if there's multiple pairs, we would have those wired in series like that, etc. The model was called enhanced self-correcting for purely historic reasons that maybe don't matter anymore. The model was enhanced because it had a description of hysteresis compared with earlier models that I had looked at, which did not. The hysteresis model is not great, as we talked about last semester, but it's better than not including this model at all. It's self-correcting in the sense that the model voltage converges to OCV plus hysteresis on a rest profile and to OCV plus hysteresis plus a steady state resistance on a constant current event, which again was different from some of the previous models I had looked at. Both of these are desirable characteristics in a model. The transient behavior is not guaranteed, and in fact it will be wrong because the model is a simplified version of what is actually happening in this cell, but we found that it was not bad. We could get quite good predictions of current to voltage behavior using this fairly simple model of a battery cell. The parameters, the R0, C1, R1, etc., are analogs to physical properties of diffusion processes, but they don't directly describe something physical. So they try to describe how the physical process behaves, but not how it works, not how it operates. Whereas the physics-based models tried to describe how the physical diffusion processes actually operated. The numeric values of these parameters are chosen to make the model predictions fit the cell test data. They don't come from direct physical measurements. They come from a curve fit or an optimization process. And we find that we get the best fits when the parameter values are functions of state of charge and furthermore functions of temperature. So the enhanced self-correcting model comprises certain equations. And these equations include a state of charge equation in the state equation itself. So this is part of a vector state equation. So it says the new state of charge equals the old state of charge minus coulombic efficiency times current times the sampling period, all divided by the capacity of this cell. This capacity is the total capacity. We'll look at distinctions between different types of capacity later in the course. I think it's chapter 4. But this is measured in ampere seconds, which is equal to coulombs. If we have a cell capacity in ampere hours, we will have to convert between hours and seconds in this equation. The parallel resistor capacitor circuits try to model diffusion, and the current through the resistor in those circuits we said was I sub R1, and the new current is related to the old current via this exponential term, a constant, and then plus 1 minus the same exponential term times the input current is the forcing value of this equation. Furthermore, we had a hysteresis equation which said that the new hysteresis was something, a hysteresis factor times the old hysteresis plus 1 minus the hysteresis factor times the sine of the input current. The hysteresis factor, notice, is a function of current, which makes this a nonlinear equation. It looks sort of linear, but it's not a linear equation at all. We are not limited to a single resistor capacitor pair. We can have multiples. If we do have multiples, we can make a vector version called I sub R, where this would be, the top one would be I sub R1, then I sub R2, then I sub Rn, if I had n of them, would be a diagonal matrix that we'll call A sub Rc times the IR vector plus B sub Rc times the input current. So I could have as many of those as I want. The trade-off is the more of these I have, the better it's possible to simulate battery behavior, but it's also more difficult to come up with system identification of the RC factors. And it also makes the simulation slower because there's more equations in the simulation. If I define A sub hk to be the time-varying hysteresis factor, then I can put all of these equations into a matrix vector form, and we get the overall state equation of the model to look like this, where state of charge, new state of charge, is 1 times old state of charge minus this Coulomb counting factor times current. The resistor currents and the RC branches are that diagonal A matrix times the previous resistor currents plus the B matrix times the current again, and the hysteresis is the hysteresis factor times the previous hysteresis state plus 1 minus the hysteresis factor times the sign of the input current. So we can organize the equations nicely for writing them in a mathematical form. So xk we define to be the state. This whole thing we call xk, and I can say that the new state is a current varying, time varying A matrix times the previous state plus a current varying, time varying B matrix times the input current. This is the enhanced self-correcting model state equations. It describes all dynamic effects, things that occur over time as opposed to instantly. The effects unwrap over time. There's an output equation to this model which computes cell voltage. Voltage is open circuit voltage plus hysteresis minus the capacitance voltages and minus the voltage drop over the series resistance. The open circuit voltage is a function of the state of charge of this cell also. So we can define a constant matrix C that has 0 in the location corresponding to the state of charge state. It has the RC resistances in locations corresponding to the diffusion resistor locations, and it has the hysteresis magnitude and the location corresponding to the hysteresis state. We can define a D matrix, which is minus R0, and we get this equation. V of k, cell voltage, is equal to open circuit voltage evaluated at the state of charge. That's not changed. But then the other terms in the voltage equation are linear products of the state and the input current. So I've got a nonlinear part, which is OCV, and then I've got a linear part, which is everything else. So the enhanced self-correcting model looks similar to, but it's not exactly the same as, a linear state space system, which we saw last course when we were reviewing the discrete time, or introducing the discrete time realization algorithm, that looks like this. This is a standard model form used in control systems literature and other places also, where we have new state equals A times old state plus B times input, and Y equals C times old state plus D times input. We have something that looks a lot like that, except our A matrix is not dependent on time only, it depends also on current, and our input includes the sign of the current as well as the current. And so there's some differences from this form, but we can still take advantage of a lot of literature that is developed using this linear state space form, and then try to generalize that literature to apply to the form that we actually do have. And we will see that a lot, especially in chapters 3 and 4 of these notes. So the dependencies of A and B on I and the open circuit voltage term and the output make the equations that we're actually working with nonlinear as opposed to linear, but the nonlinear state space form is conducive to applying control systems concepts, and that's what we do a lot of in this course. Now, we teach the concepts too. Don't get worried up front. We're going to teach these concepts, but know that that we're not making this up just for batteries. This is the concepts that we use for the state of charge estimation and state of health estimation are things that have been applied since the 1960s with a great deal of success to lots and lots of applications. So there's a very rich literature and a lot of application that says these things really work. It's not just something that is brand new and made up and we don't know about. In the last course, we talked about how to find the unknown model parameter values. We're going to omit that discussion here. We do mention briefly the process, but not the details. So to find the model, we first do some open circuit voltage testing. You might remember that involves some slow charging and slow discharging of a battery cell, and that gave us test data. And from that test data, essentially, we find a discharge voltage versus SOC and a charge voltage versus SOC, and we average them together, essentially, to get an open circuit voltage relationship for this cell, which is OCV as a function of state of charge. We also do some dynamic testing where we exercise this cell with very active current versus time profiles, and that gives us more test data. And that test data, combined with the open circuit voltage relationship that we've already seen, is processed using an optimization procedure which attempts to find resistor values and capacitor values and hysteresis values. And overall, we get an enhanced self-correcting cell model set of parameter values that describes the operation of this cell in rest situations and in active simulation situations. Then when we wish to use the model, we simulate by taking the present cell current, the state of the model, the initial state, the cell model parameters themselves. From here, we simulate the equations, and that gives us predicted voltage. So that is our review of the model for the time being. We're going to look next at a brief review of the physics-based model. It's not our focus for the course, but we will refer to it from time to time, so it's good to remember it. And then we will jump into some applications of simulating an example load that the cell might be connected to, and simulating different behaviors of battery cells that we did not look too carefully at last course, and that will again enhance our review of the model itself. These new applications will cause us to go back and review how the model works, and I think that will be good before proceeding into the next chapters.